CIET and CERT presents audiobook Ganit Prakash, textbook of mathematics for grade 7.
Chapter 7 A Tale of Three Intersecting Lines. Page number 146. On the right side of the page, a QR code is provided, scanning which additional resources to this chapter can be reached out. A triangle is the most basic closed shape. As we know, it consists of three corner points that we call the vertex of the triangle and three line segments or the sides of the triangle that join the pairs of vertices. Triangles come in various shapes. Some of them are given here. Here on this page we have picture of four triangles, namely triangle ABC, triangle XYZ, triangle UVW, triangle BAU. Observe the symbol used to denote a triangle and how the triangles are named using their vertices. While naming a triangle, the vertices can come in any order. The three sides meeting at the corners give rise to three angles that we call the angles of the triangle. For example, in triangle ABC, these angles are angle CAB, angle ABC, angle BCA, which we simply denote as angle A, angle B, and angle C respectively. What happens when the three vertices lie on a straight line? 7.1 Equilateral triangles. Among all the triangles, the equilateral triangles are the most symmetric ones. These are triangles in which all the sides are of equal lengths. Let us try constructing them. Construct a triangle in which all the sides are of length 4 centimeters. Page number 147. How did you construct this triangle and what tools did you use? Can this construction be done only using a marked ruler and a pencil? Constructing this triangle using just a ruler is certainly possible, but this might require several trials. Say we draw the base. Let us call it AB of length 4 centimeters as given in the figure here, and mark the third point C using a ruler such as AC is equal to 4 centimeters. This may not lead to BC, also having a length of 4 centimeters. If this happens, we will have to keep making attempts to mark C till we get BC to be 4 centimeter long. In the figure given here, we have a triangle ABC with sides AB is equal to 4 centimeters, AC is equal to 4 centimeters and BC is equal to 4 centimeters. How do we make this construction more efficient? Recall solving a similar problem in the previous year using a compass. In the chapter Playing with Constructions, we had to mark the top point of a house, which is 5 centimeters from two other points. The method we used to get that point can also be used here. After constructing AB is equal to 4 centimeters, we can do the following. Step 1. Using a compass, construct a sufficiently long arc of radius 4 centimeters from A, as given in the figure. The point C is somewhere on this arc. How do we mark it? Here on this page, we have a figure given with a point A and a circle with radius AB is equal to 4 centimeters. Page number 148. Step 2. Construct another arc of radius 4 centimeters from B. We have a figure on this page with AB is equal to 4 centimeters and two circles each with center A and B respectively. Let C be the point of intersection of the arcs. The construction ensures that both AC and BC are of length 4 centimeters. Can you think why? Step 3. Join AC and BC to get the required equilateral triangle. We have another picture given here with two circles forming an equilateral triangle of side length 4 centimeters. 7.2. Constructing a triangle when its sides are given. How do we construct triangles that are not equilateral? Construct a triangle of side length 4 centimeters, 5 centimeters and 6 centimeters. As in the previous case, this triangle can also be constructed using just a marked ruler, but it will involve several trials. Page number 149. How do we construct this triangle more efficiently? Choose one of the given lengths to be the base of the triangle, say 4 centimeters. Draw the base. Let A and B be the base vertices and call the third vertex C. Let AC is equal to 5 centimeters and BC is equal to 6 centimeters. We have a figure 7.1 of a line segment AB of length 4 centimeters. Like we did in the case of equilateral triangles, let us first get all the points that are at a 5 centimeter distance from A. These points lie on the circle whose center is A and has radius 5 centimeters. The point C must lie somewhere on this circle. How do we find it? Here we have another figure 7.2 with the line segment AB is equal to 4 centimeters and a circle of radius AC is equal to 5 centimeters. We will make use of the fact that the point C is 6 centimeters away from B. Construct an arc of radius 6 centimeters from B. Here we have another figure 7.3 with line segment AB is equal to 4 centimeters, a circle of radius AC is equal to 5 centimeters and another circle of radius BC is equal to 6 centimeters. Page number 150. The required point C is one of the points of intersection of the two circles. The reason why the point of intersection is the third vertex is the same as for equilateral triangles. This point lies on both the circles. Hence, its distance from A is the radius of the circle centered at A, 5 centimeters, and its distance from B is the same as the radius of the circle centered at B, 6 centimeters. Let us summarize the steps of construction, noting that constructing full circles is not necessary to get the third vertex, as given in figure 7.2 and 7.3. Here on the right side of the page, we have a figure of a triangle ABC with sides AB is equal to 4 centimeters, AC is equal to 5 centimeters and BC is equal to 6 centimeters formed by two circles, one with center A and other with center B. Step 1. Construct the base AB with one of the side lengths. Let us choose AB is equal to 4 centimeters, as given in figure 7.1. Step 2. From A, construct a sufficiently long arc of radius 5 centimeters, as given in figure 7.2. Step 3. From B, construct an arc of radius 6 centimeters such that it intersects the first arc, as given in figure 7.3. Step 4. The point where both the arcs meet is the required third vertex C. Join AC and BC to get triangle ABC. Construct. Construct triangles having the following side lengths. All the units are in centimeters. A. 4, 4, 6. B. 3, 4, 5. C. 1, 5, 5. D. 4, 6, 8. E. 3.5, 3.5, 3.5. We have learned that triangles having all three equal sides are called equilateral triangles. Those having two equal sides are called isosceles triangles. Figure it out. Question number 1. Use the points on the circle and oblique or the center to form isosceles triangles. Here we have a figure of a circle with a center point. Page number 151. Question number 2. Use the points on the circles and oblique or their centers to form isosceles and equilateral triangles. The circles are of the same size. We have figure on this page with two circles of equal radii having centers A and B. We have another figure with three circles of equal radii having centers A, B and C. Are triangles possible for any lengths? Can one construct triangles having any given side length? Are there lengths for which it is impossible to construct a triangle? Let us explore this. Construct a triangle with side lengths 3 cm, 4 cm and 8 cm. What is happening? Are you able to construct the triangle? Here is another set of lengths 2 cm, 3 cm and 6 cm. Check if a triangle is possible for these side lengths. Try to find more sets of lengths for which a triangle construction is impossible. Think if you can find any pattern in them. We notice that a triangle is possible for some sets of lengths and not possible for others. How do we check if a triangle exists for a given set of lengths? One way is to actually try to construct the triangle and check if it is possible. Is there a more efficient way to check this? Triangle inequality. Consider the lengths 10 cm, 15 cm and 30 cm. Does there exist a triangle having these as side lengths? To tackle this question, let us study a property of triangles. Imagine a small plot of plain land having a tent, a tree and a pole. Imagine you are at the entrance of the tent and want to go to the tree. Which is the shorter path? First, a straight line path to the tree, that is the red path, or second, the straight line path from the tent to the pole, followed by the straight line path from the pole to the tree, the yellow path. Page number 152. Clearly, the direct straight line path from the tent to the tree is shorter than the roundabout path via the pole. In fact, the direct straight line path is the shortest possible path to the tree from the tent. Here we have a picture in which there is a tent, a tree and a pole. Two kids are looking for the shortest path in red between tent and tree and other paths in yellow from tent to the pole and then from pole to the tree. Will the direct path between any 2 points be shorter than the roundabout path via a third point? Clearly, the answer is yes. Can this understanding be used to tell something about the existence of a triangle having side lengths 10 cm, 15 centimeters and 30 centimeters. Let us suppose that there is a triangle for this set of lengths. Remember that at this point, we are not sure about the existence of the triangle, but we are only supposing that it exists. Let us draw a rough diagram. Here, we have a figure 7.4 of triangle ABC with side lengths BC is equal to 10 centimeters, AB is equal to 15 centimeters and AC is equal to 30 centimeters. Page number 153. Does everything look right with this triangle? If this triangle were possible, then the direct path between any two vertices should be shorter than the roundabout path via the third vertex. Is this true for our rough diagram? Let us consider the paths between B and C. Direct path length is equal to BC is equal to 10 centimeters. What is the length of the roundabout path via the vertex A? It is the sum of the lengths of line segments BA and AC. Roundabout path length is equal to BA plus AC is equal to 15 centimeters plus 30 centimeters is equal to 45 centimeters. Is the direct path length shorter than the roundabout path length? Yes. Let us now consider the paths between A and B. Direct path length is equal to AB is equal to 15 centimeters. Finding the length of the roundabout path via the vertex C, we get roundabout path length is equal to AC plus CB is equal to 30 centimeters plus 10 centimeters is equal to 40 centimeters. Is the direct path length shorter than the roundabout path length? Yes. Finally, consider paths between C and A. Direct path length is equal to CA is equal to 30 centimeters. Roundabout path length is equal to CB plus BA is equal to 10 centimeters plus 15 centimeters, that is equal to 25 centimeters. Is the direct path length shorter than the roundabout path length? In this case, the direct path is longer, which is absurd. Can such a triangle exist? No. Therefore, a triangle having side length 10 centimeters, 15 centimeters and 30 centimeters cannot exist. We are thus able to find without construction why a triangle for the set of lengths 10 centimeters, 15 centimeters and 30 centimeters cannot exist. We have been able to figure this out through spatial intuition and reasoning. Recall how we used similar intuition and reasoning to discover properties of intersecting and parallel lines. We will continue to do this as we explore geometry. Can we say anything about the existence of a triangle having side lengths 3 centimeters, 3 centimeters and 7 centimeters? Verify your answer by construction. In the rough diagram in figure 7.4, is it possible to assign lengths in a different order such that the direct paths are always coming out to be shorter than the roundabout paths? If this is possible, then the triangle might exist. Is such rearrangement of lengths possible in the triangle? Here, there is a picture of a girl who is thinking. Page number 154. Figure it out. Question number 1. We checked by construction that there are no triangles having side lengths 3 centimeters, 4 centimeters and 8 centimeters and 2 centimeters, 3 centimeters and 6 centimeters. Check if you could have found this without trying to construct the triangle. Question number 2. Can we say anything about the existence of a triangle for each of the following sets of lengths? A. 10 kilometers, 10 kilometers and 25 kilometers. B. 5 millimeters, 10 millimeters and 20 millimeters. C. 12 centimeters, 20 centimeters and 40 centimeters. You would have realized that using a rough figure and comparing the direct path lengths with their corresponding roundabout path lengths is the same as comparing each length with the sum of the other two lengths. There are three such comparisons to be made. Question number 3. For each set of lengths seen so far, you might have noticed that in at least two of the comparisons, the direct length was less than the sum of the other two. If not, check again. For example, for the set of lengths 10 centimeters, 15 centimeters and 30 centimeters, there are two comparisons where this happens. 10 is less than 15 plus 30. 15 is less than 10 plus 30. But this doesn't happen for the third length. 30 is greater than 10 plus 15. Will this always happen? That is, for any set of lengths, will there be at least two comparisons where the direct length is less than the sum of the other two? Explore for different set of lengths. Further, for a given set of lengths, is it possible to identify which lengths will immediately be less than the sum of the other two without calculations? Hint: consider the direct lengths in the increasing order. Given three side lengths, what do we need to compare to check for the existence of a triangle? When each length is smaller than the sum of the other two, we say that the lengths satisfy the triangle inequality. For example, the set 3, 4, 5 satisfies the triangle inequality, whereas the set 10, 15, 30 does not satisfy the triangle inequality. We have found that the lengths such as 10, 15, 30 that do not satisfy the triangle inequality cannot be the side lengths of a triangle. Page number 155. Does a triangle exist with side lengths 4 centimeters, 5 centimeters and 8 centimeters? This satisfies the triangle inequality. 8 is less than 4 plus 5, that is equal to 9. Why do we not need to check the other two sides? This means that all the direct path lengths are less than the roundabout path lengths. Does this confirm the existence of a triangle? If one of the direct path lengths had been longer, we could have concluded that a triangle would surely not exist. But in this case, we can only say that a triangle may or may not exist. For the triangle to exist, the arcs that we construct to get the third vertex must intersect. Is it possible to determine that this will happen without actually carrying out the construction? Visualizing the construction of circles. Let us imagine that we start the construction by constructing the longest side as the base. Let AB be the base of the length 8 centimeters. The next step is the construction of sufficiently long arcs corresponding to the other two lengths 4 centimeters and 5 centimeters. Instead of just constructing the arcs, let us complete the full circles. Suppose we construct a circle of radius 4 centimeters with A as the center. Here we have a line segment AB of length 8 centimeters and a circle with center A having radius 4 centimeters in the figure. Now, suppose that a circle of radius 5 centimeters is constructed, centered at B. Can you draw a rough diagram of the resulting figure? Note that in the figure given, AX is equal to 4 centimeters and AB is equal to 8 centimeters. So, what is BX? Does this length help in visualizing the resulting figure? Page number 156. Since BX is equal to 4 centimeters and the radius of the circle centered at B is 5 centimeters, it is clear that the circles will intersect each other at 2 points. Here we have figure 7.5 in which AX is equal to 4 centimeters, AB is equal to 8 centimeters and BX is equal to 5 centimeters, and the circles are intersecting each other at 2 points. What does this tell us about the existence of a triangle? The points A and B, along with either of the points of intersection of the circles, will give us the required triangle. Thus, there exists a triangle having side length 4 centimeters, 5 centimeters and 8 centimeters. Figure it out. Question number 1. Which of the following lengths can be the side lengths of a triangle? Explain your answers. Note that for each set, the three lengths have the same unit of measure. A 2, 2, 5, B 3, 4, 6, C 2, 4, 8, D 5, 5, 8, E 10, 20, 25, F 10, 20, 35, G 24, 26, 28. We observe from the previous problems that whenever there is a set of lengths satisfying the triangle inequality, each length less than sum of the other two lengths, there is a triangle with those three lengths as side lengths. Will triangles always exist when a set of lengths satisfy the triangle inequality? How can we be sure? Page number 157. We can be sure of the existence of a triangle only if we can show that the circles intersect internally, as in the figure 7.5, whenever the triangle inequality is satisfied. But are there other possibilities when the two circles are constructed? Let us visualize and study them. The following different cases can be conceived. Here, there are three figures given. In case 1, two circles with center A and B touch each other externally at a point. In case 2, circles do not intersect. In case 3, circles intersect each other internally at 2 points. Note that while constructing the circles, we take A, the length of the base AB is equal to longest of the given length, B, the radii of the circles to be the smaller two lengths. Which of the above mentioned cases will lead to the formation of a triangle? Clearly, triangles are formed only when the circles intersect each other internally. That is case 3. Let us study each of these cases by finding the relation between the radii, the smaller two lengths, and AB longest length. Case 1. Circles touch each other at a point. For this case to happen, sum of the two radii is equal to AB, or sum of the two smaller length is equal to longest length. Page number 158. Here there is a figure in which the two circles touch each other externally at a point X. In the case 2, circles do not intersect internally. For this case to happen, what should be the relation between the radii and AB? It can be understood from the figure that sum of the two radii is less than AB, or sum of the two smaller length is less than longest length. Here we have a picture in which two circles do not intersect each other, each having center A and B respectively. Case 3. Circles intersect each other. Here we have a picture in which two circles intersect each other at 2 points. The two circles have different radii. Page number 159. AB is composed of one radius and a part of the other. So, sum of the two radii is greater than AB, or sum of the two smaller length is greater than longest length. Can we use this analysis to tell if a triangle exists when the lengths satisfy the triangle inequality? If the given lengths satisfy the triangle inequality, then the sum of the two smaller length is greater than the longest length. This means that this will lead to case 3 where the circles intersect internally and so a triangle exists. How will the two circles turn out for a set of lengths that do not satisfy the triangle inequality? Find 3 examples of sets of lengths for which the circles A. touch each other at a point, B. do not intersect. Frame a complete procedure that can be used to check the existence of a triangle. Conclusion: if a given set of 3 lengths satisfies the triangle inequality, then the triangle exists, having those as side lengths. If the set does not satisfy the triangle inequality, then a triangle with those side lengths does not exist. Figure it out. Question number 1. Check if a triangle exists for each of the following set of lengths: A 1, 100, 100, B 3, 6, 9, C 1, 1, 5, D 5, 10, 12. Question number 2. Does there exist an equilateral triangle with sides 50, 50, 50? In general, does there exist an equilateral triangle of any side length? Justify your answer. Question number 3. For each of the following, give at least 5 possible values for the third length. So there exists a triangle having these as side lengths. Decimal values could also be chosen. A 1, 100, B 5, 5, C 3, 7. Page number 160. Check if you can describe all possible lengths of the third side in each case so that a triangle exists with those side lengths. For example, in case A, all numbers strictly between 99 and 101 would be possible. 7.3. Construction of triangles when some sides and angles are given. We have learnt how to construct triangles when their side lengths are given. Now, we will take up constructions where in place of some side lengths, angle measures are given. Two sides and the included angle. How do we construct a triangle if two sides and the angle included between them are given? Here are some examples of measurements indicating the included angle. There are figures of 3 triangles here. In the first one, the sides of the triangle are 3 centimeters and 4 centimeters with the angle included between them as 60 degrees. In the second one, the side lengths of the triangle are 5 centimeters and 6 centimeters with the included angle 30 degrees. In the third one, we have a triangle with side lengths 2 centimeters and 3 centimeters and the angle included between them as 40 degrees. Construct a triangle ABC with AB is equal to 5 centimeters, AC is equal to 4 centimeters and angle A is equal to 45 degrees. Let us take one of the given sides AB as the base of the triangle. Here we have another figure with measure of sides as 4 centimeters and 5 centimeters. The angle between them is 45 degrees. Step 1. Construct a side AB of length 5 centimeters. Step 2. Construct angle A is equal to 45 degrees by drawing the other arm of the angle. Step 3. Mark the point C on the other arm such that AC is equal to 4 centimeters. Step 4. Join BC to get the required triangle. Here we have a figure of a triangle with side length AB is equal to 5 centimeters, AC is equal to 4 centimeters, and the angle between the side length as 45 degrees. Page number 161. Figure it out. Question number 1. Construct triangles for the following measurements where the angle is included between the sides. A. 3 centimeters, 75 degrees, 7 centimeters. B. 6 centimeters, 25 degrees, 3 centimeters. C. 3 centimeters, 120 degrees, 8 centimeters. We have learned that triangles do not exist for all sets of side lengths. Is there a combination of measurements in the case of two sides and the included angle where a triangle is not possible? Justify your answer using what you observe during construction. Two angles and the included side. In this case, we are given two angles and the side that is a part of both angles, which we call the included side. Here are some examples of such measurements. We have three different figures. In the first one, we have a triangle with angle measures as 40 degrees and 50 degrees, and the side included between them is 5 centimeters. In the second figure, we have a triangle in which the measures of the angles are 30 degrees and 45 degrees, and the side length is 4 centimeters. In the third one, we have the measures of the angles as 50 degrees and 20 degrees, and the side which is included between the angles is of length 6 centimeters. Construct a triangle ABC where AB is equal to 5 centimeters, angle A is equal to 45 degrees, and angle B is equal to 80 degrees. Let us take the given side as the base. Here we have a figure in which AB is 5 centimeters and angle A is 45 degrees and angle B is 80 degrees. Step 1. Draw the base AB of length 5 centimeters. Step 2. Draw angle A and angle B of measures 45 degrees and 80 degrees respectively. Step 3. The point of intersection of the two new line segments is the third vertex C. Here we have a figure in which the triangle ABC has the measurements as AB is equal to 5 centimeters, angle A is 45 degrees, and angle B is 80 degrees. Page number 162. Figure it out. Question number 1. Construct triangles for the following measurements. A. 75 degrees, 5 centimeters, and 75 degrees. B. 25 degrees, 3 centimeters, 60 degrees. C. 120 degrees, 6 centimeters, 30 degrees. Do triangles always exist? Do triangles exist for every combination of two angles and their included side? Explore. As in the case when we are given all three sides, it turns out that there is not always a triangle for every combination of two angles and the included side. Find examples of measurements of two angles and the included side where a triangle is not possible. Let us try to visualize such a situation. Once the base is drawn, try to imagine how the other sides should be so that they do not meet. Here are some obvious examples. Here we have three figures with base lines and with angles greater than 90 or equal to 90. If two angles are greater than or equal to a right angle, that is 90 degrees, then it is clear that a triangle is not possible. Now we make one of the base angles an acute angle, say 40 degrees. What are the possible values that the other angle should take so that the lines don't meet? Here we have a figure in which the angle between AB and AC is 40 degrees. It is clear that if the line from B is inclined sufficiently to the right, then it will not meet the line L. A. Try to find a possible angle B marked in the figure for this to happen. B. What could be smallest value of angle B for the lines to not meet? Page number 163. Here we have a figure with side length AB and angle BAC as 40 degrees, and we have four lines with different angles and one angle in blue which is parallel to AC. The blue line is the line with the least rightward bend that doesn't meet the line L. Visually, it is clear that the line that creates the smallest angle B has to be the one parallel to L. Let us call this parallel line M. Can you tell the actual value of angle B in this case? Note that AB is the transversal. We have seen that when two lines are parallel, the internal angles on the same side of the transversal adds up to 180 degrees. So, angle B is equal to 140 degrees. So, for what values of angle B does a triangle not exist? Does the length AB play any part here? From the discussion above, it can be seen that the length AB does not play any part in deciding the existence of a triangle. We can say that a triangle does not exist when angle B is greater than or equal to 140 degrees. Figure it out. Question number 1. For each of the following angles, find another angle for which a triangle is A. Possible, B. Not possible. Find at least two different angles for each category. A. 30 degrees, B. 70 degrees, C. 54 degrees, D. 144 degrees. Question number 2. Determine which of the following pairs can be the angles of a triangle and which cannot. A. 35 degrees, 150 degrees. B. 70 degrees, 30 degrees. C. 90 degrees, 85 degrees. D. 50 degrees, 150 degrees. Like the triangle inequality, can you form a rule that describes the two angles for which a triangle is possible? Can the sum of the two angles be used for framing this rule? Page number 164. When the sum of two given angles is less than 180 degrees, the triangle exists with these angles. If the sum is greater than or equal to 180 degrees, there is no triangle with these angles. Let us take two angles, say 60 degrees and 70 degrees, whose sum is less than 180 degrees. Let the inclined side be 5 centimeters. What could the measure of the third angle be? Does this measure change if the base length is changed to some other value, say 7 centimeters? Construct and find out. In general, once the two angles are fixed, does the third angle depend on the included side length? Try with different pairs of angles and lengths. The measurements might show that the side length has no effect or a very small effect on the third angle. With this observation, let us see if we can find the third angle without carrying out the construction and measurement. Try experimenting with different triangles to see if there is a relation between any two angles and the third angle. To find this relation, what data will you keep track of and how will you organize the data you collect? Consider a triangle ABC with angle B is equal to 50 degrees and angle C is equal to 70 degrees. Let us find out how we can find angle A without construction. Here we have a figure of triangle ABC with angles B marked as 50 degrees and angle C marked as 70 degrees. We learned that the notion of parallel lines was useful to determine that the sum of any two angles of a triangle is less than 180 degrees. Parallel lines can be used to find the third angle, angle BAC as well. Let us suppose we construct a line XY parallel to BC through the vertex A. We can find new angles being formed here, angle XAB and angle YAC. What are their values? Here in figure 7.6, we have a triangle ABC with angle B as 50 degrees and angle C as 70 degrees. And there's a line parallel to BC passing through A as XY. We are supposed to find out the value of XAB and angle YAC. Since the line XY is parallel to BC, angle XAB is equal to angle B and angle YAC is equal to angle C because they are alternate angles of the transversals AB and AC. Page number 165. Therefore, angle XAB is equal to 50 degrees and angle YAC is equal to 70 degrees. Can we find angle BAC from this? We know that angle XAB, angle YAC and angle BAC together form 180 degrees. So, angle XAB plus angle YAC plus angle BAC is equal to 180 degrees. 50 degrees plus angle BAC plus 70 degrees is equal to 180 degrees. 120 degrees plus angle BAC is equal to 180 degrees. Thus, angle BAC is equal to 60 degrees. Now, construct a triangle taking BC to be of any suitable length and verify if this is indeed the case. Figure it out. Question number 1. Find the third angle of a triangle using a parallel line when two of the angles are A. 36 degrees, 72 degrees, B. 150 degrees, 15 degrees, C. 90 degrees, 30 degrees, D. 75 degrees, 45 degrees. Question number 2. Can you construct a triangle all of whose angles are equal to 70 degrees? If two of the angles are 70 degrees, what would be the third angle? If two of the angles are 70 degrees, what would the third angle be? If all the angles in a triangle have to be equal, then what must its measure be? Explore and find out. Question number 3. Here is a triangle in which we know angle B is equal to angle C and angle A is equal to 50 degrees. Can you find angle B and angle C? Here we have a figure of triangle ABC with angle A marked as 50 degrees. Angle sum property. What can we say about the sum of the angles of any triangle? Consider a triangle ABC. To find the sum of its angles, we can use the same method of drawing a line parallel to the base. Construct a line through A that is parallel to BC. Page number 166. We need to find angle A plus angle B plus angle C. We know that angle B is equal to angle XAB, angle C is equal to angle YAC. So, angle A plus angle B plus angle C is equal to angle A plus angle XAB plus angle YAC is equal to 180 degrees, as together they form a straight angle. Thus, we have proved that the sum of the three angles in any triangle is 180 degrees. This rather surprising result is called the angle sum property of triangles. Here, in figure 7.7, we have a triangle ABC and a line XY passing through A. We also have angles XAB and ABC in red color, and angle YAC and angle ACB in green color, and angle BAC is in brown color. Take some time to reflect upon how we figured out the angle sum property. In the beginning, the relationship between the third angle and the other two angles was not at all clear. However, a simple idea of drawing a line parallel to the base through the top vertex, as in the figure above 7.7, suddenly made the relationship obvious. This ingenious idea can be found in a very influential book in the history of mathematics called The Elements. This book is attributed to the Greek mathematician Euclid, who lived around 300 BCE. This solution is yet another example of how creative thinking plays a key role in mathematics. There is a convenient way of verifying the angle sum property by folding a triangular cutout of a paper. Do you see how this shows that the sum of the angles in this triangle is 180 degrees? Here we have a figure in which a triangular cutout is folded and is showing that sum of three angles of a triangle is 180 degrees. Page number 167. Exterior angles. The angle formed between the extension of a side of a triangle and the other side is called an exterior angle of the triangle. In this figure, angle ACD is an exterior angle. Here we have a figure in which triangle ABC has an exterior angle as angle ACD marked. Find angle ACD if angle A is equal to 50 degrees and angle B is equal to 60 degrees. From the angle sum property, we know that 50 degrees plus 60 degrees plus angle ACB is equal to 180 degrees. 110 degrees plus angle ACB is equal to 180 degrees. So, angle ACB is equal to 70 degrees. So, angle ACD is equal to 180 degrees minus 70 degrees is equal to 110 degrees. Since angle ACB and angle ACD together form a straight angle, find the exterior angle for different measures of angle A and angle B. Do you see any relation between the exterior angle and these two angles? Hint: from angle sum property, we have angle A plus angle B plus angle ACB is equal to 180 degrees. We also have angle ACD plus angle ACB is equal to 180 degrees. Since they form a straight angle, what does this show? 7.4. Constructions related to altitudes of triangles. There is another set of useful measurements with respect to a triangle: the height of each of its vertices with respect to the opposite sides. In the world around us, we talk of the heights of various objects: the height of a person, the height of a tree, the height of a building, etc. What do we mean by the word height? Consider a triangle ABC. What is the height of the vertex A from its opposite side BC, and how can it be measured? Let AD be the line segment from A drawn perpendicular to BC. The length of AD is the height of the vertex A from BC. The line segment AD is said to be one of its altitudes of the triangle. Here we are given in figure 7.8 a triangle ABC with AD as the altitude marked as 90 degrees. Page number 168. The other altitudes are BE and CF in the figure given. The perpendiculars drawn from the other vertices to their respective opposite sides. In the figure, we have a triangle ABC in which CF and BE are the corresponding altitudes. Whenever we use the word height of the triangle, we generally refer to the length of the altitude to whatever side we take as base. This altitude is AD in the case of figure 7.8. What would the altitude from A to BC be in this triangle? Here we are provided an obtuse angle triangle ABC. In another picture, we have the altitude which is shown outside the triangle as altitude AD when BC is extended. We extend BC and then drop the perpendicular from A to this line. Altitudes using paper folding. Cut out a paper triangle. Fix one of the sides as the base. Fold it in such a way that the resulting crease is an altitude from the top vertex to the base. Justify why the crease formed should be perpendicular to the base. Construction of the altitudes of a triangle. Construct an arbitrary triangle. Label the vertices A, B, C, taking BC to be the base. Construct the altitude from A to BC. Constructing the altitude using just a ruler is not accurate. To get a more precise angle of 90 degrees, we use a set square along with a ruler. Can you see how to do this? Page number 169. Step 1. Keep the ruler aligned to the base. Place the set square on the ruler as given such that one of the edges of the right angle touches the ruler. Here we have a figure in which set square is placed along a ruler in a sliding position on the base BC of the triangle. Step 2. Slide the set square along the ruler till the vertical edge of the set square touches the vertex A. This can be seen in the next figure given here. We have a ruler and a set square sliding along the triangle ABC. Step 3. Draw the altitude to BC through A using the vertical edge of the set square. Does there exist a triangle in which a side is also an altitude? Visualize such a triangle and draw a rough diagram. We find that this happens in triangles where one of the angles is a right angle. Triangles having one right angle is called right angle triangles or simply right triangles. Altitude from A to BC. Here in the figure, it is given that triangle ABC has AB as the altitude, so angle B is 90 degrees. The triangle ABC is a right angle triangle. Page number 170. 7.5. Types of triangles. In our study of triangles, we have encountered the following types of triangles: equilateral, isosceles, scalene, and right angle triangles. Did you spot any other type of triangle? The classification of triangles as equilateral and isosceles was based on equality of sides. Equilateral triangles have sides of equal length. Isosceles triangles have two sides of equal length. Scalene triangles have sides of three different lengths. Here we are given three different pictures. One is of an equilateral triangle having three sides equal. Second one is of isosceles triangle with two sides equal, and the third one is of a scalene triangle having three sides of different measures. Can a similar classification be done based on equality of angles? Is there any relation between these two classifications? We will answer these questions in a later chapter. We used angle measures when classifying a triangle as a right angle triangle. What are the other types of triangles based on angle measures? A classification of triangles based on their angle measures is acute-angled, right-angled, and obtuse-angled triangles. We have already seen what a right angle triangle is. It is a triangle with one right angle. Similarly, an obtuse angle triangle has one obtuse angle. What could an acute angle triangle be? Can we define it as a triangle with one acute angle? Why not? In an acute angle triangle, all three angles are acute angles. Figure it out. Question number 1. Construct a triangle ABC with BC is equal to 5 centimeters, AB is equal to 6 centimeters, CA is equal to 5 centimeters. Construct an altitude from A to BC. Question number 2. Construct a triangle TRY with RY is equal to 4 centimeters, TR is equal to 7 centimeters, angle R is equal to 140 degrees. Construct an altitude from T to RY. Page number 171. Question number 3. Construct a right angle triangle ABC with angle B is equal to 90 degrees, AC is equal to 5 centimeters. How many different triangles exist with these measurements? Hint: note that the other measurements can take any values. Take AC as the base. What values can angle A and angle C take so that the other angle is 90 degrees? Question number 4. Through construction, explore if it is possible to construct an equilateral triangle, that is, first one, right angled, second, obtuse angled. Also construct an isosceles triangle, that is, first, right angled, second, obtuse angled. Summary. First point. Use of a compass simplifies the construction of triangles when the side lengths are given. Second point. A set of three lengths where the length of each is smaller than the sum of the other two is said to satisfy the triangle inequality. Point number 3. Side lengths of a triangle satisfy triangle inequality, and if a given set of lengths satisfy the triangle inequality, a triangle can be constructed with those side lengths. Point number 4. Triangles can be constructed when the following measurements are given: A. 2 of the sides and their included angle, B. 2 angles and the included side. Fifth point. The sum of the angles of a triangle is always 180 degrees. Sixth point. An altitude of a triangle is a perpendicular line segment from a vertex to its opposite side. Point number 7. Equilateral triangles have sides of equal length. Isosceles triangles have two sides of equal length. Scalene triangles have sides of three different lengths. Point number 8. Triangles are classified based on their angle measures as acute-angled, right-angled, and obtuse-angled triangles. Page number 172. Puzzle time. Shortest path in a box. There is a spider in a corner of a box. It wants to reach the farthest opposite corner marked in the figure. Since it cannot fly, it can reach the opposite point only by walking on the surfaces of the box. What is the shortest path it can take? Take a cardboard box and mark the path that you think is the shortest from one corner to its opposite corner. Compare the lengths of this path with that of the paths made by your friends. There is a hint provided in the picture here, and we have a box with a spider inside the box, and a point is marked where the spider has to reach. We can also find pictures of kids wondering to solve the puzzle. Chapter 7 ends here.
Ganit Prakash, you were just listening to this audiobook, Textbook of Mathematics for Grade 7. Narration Swarnlata Sharma. Sound recordist Virendra Rawat. Production assistant Soumya Malik. Directed and produced by Vimalesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.